So moving on in our discussion about nuclear chemistry, today we're going to talk about two things, radioactive decay series and half-life. So I'm going to give you a chance to pause your video and copy down these notes. Okay, so starting with radioactive decay series. These are a series of sequential reactions of alpha and beta emissions that change larger unstable nuclides to smaller stable nuclides. When we wrote our nuclear reactions last time, our equations, we just wrote one equation. But in fact, many of these nuclides, especially the ones with greater than 83 protons, because any element with more than 83 protons is radioactive, many of these with more than 83 protons go through a series of decays, a series of nuclear reactions, not just one. And that is actually illustrated in your book on page 508. Right here. And we can see if we take uranium-238, it decays many times. So thorium-234, palladium-234, uranium-234, thorium-230, and so on and so forth. And there's a lot of different pathways it can take once it gets down here. So this is a radioactive decay series here that you are looking at. And in your book, you'll see that elements can take generally 3 different paths. I'm not going to get into those. We don't need to. You just have to be aware of them, that they are there, and that oftentimes these nuclides, this is what they do. There's a series of reactions they go through. Now, do all the atoms do this all at the same time in the element? No. Okay, just one single atom at a time will follow this path, or some of them, not the whole thing, the whole sample will not go through this path at the same time, because there's something called a half-life that we're going to talk about now. Now, I did have this example that we just looked at in your book written down right here, so you can refer to that, so we didn't have to draw that. So let's talk about half-life, and don't worry about that yet. Okay, so half-life is the amount of time required for 1/2 of the nuclei in a radioactive sample to decay into another kind of nucleus. Radioactive decay does not take place all at once. What we see is that different nuclides have different half-lives, meaning that half of them break down during a certain amount of time. And we're going to take a look at table N. These are selected radioisotopes. And we can see here that these are a number of nuclides. You can see that there's the nuclide, its symbol, its half-life, its decay mode, and its name. And we can see that something like gold 198, its half-life is 2.695 days. So just shy of 3 days, and half of that will break down. And then in in about 2.7 days, half of it will break down more, and half. And that undergoes beta decay. Okay, here, francium-220, 27.4 seconds that it lasts, and that's alpha decay. Okay, we have positron decay for something like potassium-37, 1.23 seconds. Okay, so these are a lot of different half-lives that are in this table. Now, what we need to know is that the shorter the half-life is, the faster the nuclei decay. And the longer the half-life, the slower they decay. So they'll be around longer. So let's take a look at a problem. So I will let you copy down this problem. So pause the video. Okay. So how do we do this problem? So I have a 192 gram sample of thorium-234 decays for 96.4 days. At the end of this time, how much thorium-234 is left? All right. Well, the first thing we need to know, so I'm going to show you the steps in solving a problem like this. Step number 1 is we have to determine the number of half-lives. I would normally say go to your reference tables and look it up, but this one is not on your reference tables. So I will give the number to you. So determine the number of half-lives. To do this, we need to know that thorium-234 has a half-life, so a T1/2 equal to 24.1 days. From there, we do a conversion. So we're going to use our bridge notation, and we're going to start with 96.4 days. We know that 24.1 days is 1 half-life. So when we divide 96.4 by 24.1, we get 4 half-lives. The second step, so we're not there yet. We have the number of half-lives. We want to know how much of the sample is left. So step number 2 is to determine the fraction of the sample left. And that is determined using the equation 1/2 raised to the number of half-lives. And I'm going to get a new sheet of paper here. I'll leave that there for a second so you can pause, okay? All right. 1/2 to the number of half-lives. So that, in this case, is 1/2 to the 4th power, because that is equal to 1/2 times 1/2 times 1/2 times 1/2. And so basically what this means is that after 1 half-life, we have half of a sample left. And then after that half-life, we have half of that sample. And after a half-life, we have half of those other 2 halves and half again. So remember, when we do this, we don't just multiply 4 times 2 is 8. It's 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So 1/16 of the sample is left after 4 half-lives. And so then what we do, step number 3, is to determine the amount of sample left. And to do that, we multiply the fraction by the amount of sample. So we have 1/16 times the amount of sample we're given is 192 grams. When we actually divide here, 192 by 16, we get 12 grams of thorium-234 are left. So those are the steps to figure out this type of problem. So on page 512, I want you to do problems 3 and 4 following these 3 steps. I'm going to pause for a few seconds so you can stop the video. That if you want to try these on your own, you can go ahead. Here are the answers to those questions. So go ahead and pause the video and check your work if you did it. And now I'm going to show you how to do those problems. Okay, so on page 512, number 3 says, barium-122 has a half-life of 2 minutes. A fresh sample weighing 80 grams was obtained. If it takes 10 minutes to prepare the experiment, how much barium-122 remains when the experiment begins? Gotta work fast with this stuff. Okay, so 10 minutes. We know that 2 minutes is 1 half-life. So when we divide 10 by 2, we get 5 half-lives. Okay, so we take the fraction 1/2, we raise it to the 5th power. This means 1/2 times 1/2 times 1/2 times 1/2 times 1/2. So when we multiply that together, it's 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and 16 times 2 is 32. So we have 1/32 of a second of the sample left. So what we do then is we take 1/32 and multiply that by the amount of sample we started with, which was 80 grams. 80 divided by 32 is 2.5 grams of that sample are left. For number 4, the problem says, iodine-131 is used in the treatment of a hyperactive thyroid gland. The half-life of iodine-131 is 8 days. If a hospital receives a 200-gram shipment of iodine-131, how much will be left after 32 days? So we know that we start with 32 days because we have to figure out the number of half-lives. The half-life is 8 days, is 1 half-life. So 32 divided by 8 is 4 half-lives. We take 1/2, raise it to the 4th power. That's the same as 1/2 times 1/2 times 1/2 times 1/2, which is 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And 1/16 of the original sample, which was 200 grams. 200 divided by 16 is 12.5 grams. I had to do a double take because the number's awful close to number 3, isn't it? So I did a double take there, but yeah. So the steps are always the same. Find the number of half-lives. Use that to determine the fraction of the sample that's left. Multiply the amount of the original sample by the fraction. Okay, so I also would like you to do page 523, numbers 22 and 23. So go ahead and pause the video and try those, and then I'll put the answers up here. Here are the answers to those problems. I'll pause your video, check your answers. Now I will go through those problems. Okay, so for number 22, you might not have realized there was table 24. I actually had a hard time finding it at first, but this uses table 20-4 on page 508. And if you look at that table, let me get it here. Should have had the page number ready and I didn't. Okay, so just under this one. So we have this nucleus and we have the half-life. And the question is, referring to table 24, which nucleus decays more quickly, bromium-8 or magnesium-28? Excuse me, or bromine-80, not 8. Bromine-80 has a half-life of 17.6 minutes, and magnesium-28 has a half-life of 21 hours. So the answer is, and I'm just going to show you this answer here again, instead of rewriting all that. It's bromine-80 because it has a shorter half-life. Bromine-80 has a half-life of 17.6 minutes versus magnesium-28, 21 hours. So the faster the half-life, the shorter the half-life, the faster it will break down. The longer the half-life, the slower it will break down. Both of these are still pretty fast. Okay, let's do number 23. Number 23 says, the half-life of hydrogen-3 is 12.26 years. If 35.8 grams of hydrogen-3 are allowed to decay for 36.78 years, what mass of hydrogen-3 will be left? So we have to start with the number of years this is allowed to decay, which is 36.78 years. We divide that by the number of years and a half-life. And we get 3 half-lives. Now I know you could just divide. I like to use the conversion because if you use the conversion method, you never go wrong. Okay, so we take 1/2, the fraction 1/2, raise that to the third power, so that's 1/2 times 1/2 times 1/2. Now I realize you could just do this in your calculator too, but I'm showing you where it comes from. So 2 times 2 is 4, 4 times 2 is 1/8 for this. So 1/8 of the sample is left, and we started out with a 35.8 gram sample. So when all is said and done, after 3 half-lives, only 4.48 grams is left. Now guys, realize some quick checks here. If the number doesn't get smaller, you did something wrong. Okay? When you're checking your answers, use some common sense here. If you end up with a larger number than the sample you started with, you know you did something wrong because these things are decaying, they're decreasing, they're not getting larger. Okay, so always look at your answer and say, does this make sense? So, well, I'll be back with you tomorrow with some more nuclear chemistry.